All right. Hello, everyone, and welcome to Algorithms Live. This week, I'm going to be going over this Treaps data structure that I really enjoy. I'm going to kind of present this as like a more powerful segment tree. So we're going to learn how to basically do everything a segment tree can do with a Treap, explain how it's a little bit different. Treaps are randomized algorithms, so they have expected runtime of log n per insertion and things like that. So the analysis can get a little bit complicated. So I'm actually going to skip a lot of the analysis in this video. I'm just going to focus more on how to do them and like different techniques that you can use them for. And this week, I'm not actually going to do coding on this episode. I'm going to push that to next week or the week after too, maybe code a few problems with Treaps so you can just see how powerful they are. They are a little bit more involved to implement, and I want to try implementing them two different ways and just show that there's a couple different ways you can approach implementing them that are a little simpler. So this episode is going to be much more focused on just the concept of Treaps and how to use them. But if you are interested in the analysis bit, you can go to Jeff Erickson's website. Now let's see how, make sure I spell that correctly. Yeah. So if you haven't seen this before, it's algorithms.wtf. And it's got a pretty good set of Treap notes, and it can explain the runtime bounding and things. Yeah, I'll make the pen a little bit smaller this time. Another one is if you look up this paper by Brian Dean. So Brian Dean is the USACO director, if you're not familiar with him. And he wrote this paper called Randomized Reduction. And I really like this paper. It's a CSE paper. And basically, what this paper is really good for is it can just show you a bunch of different randomized algorithms and how to analyze them much more simply than just doing your typical analysis. So if you do, so he introduces this thing called the randomized reduction lemma. And you basically can analyze a whole collection of randomized algorithms and show that they have like this expected log n runtime. And what's nice about this is you just completely avoid these things called Chebyshev inequalities, which typically are confusing to some people. And if you're not very familiar with probability theory or linearity of expectations or anything like that, dealing with randomized algorithms can get really messy. So you can completely subvert all that like mathematical side and just look at this. And it's written in this really friendly way. It's not like it's a CSE paper. It's not this like deep technical paper, even though there are good technical details in it. So those are two areas I would look if you're interested in the analysis. And then the one after that, I would say, is there's pretty good at CMU. There's some pretty good notes on analyzing the runtime of Treaps. And I may do some of that in a future episode, just talking about it. But for this episode, I just want to introduce Treaps and think about them. So it's one thing that I think is important in this episode is this concept of a random binary search tree. So we have this idea of a binary search tree, and I'm kind of assuming most of you are familiar with it already. But basically, you have some elements. Something like this, maybe. And you want to insert them in a search tree. And the idea is if you have some element X, everything to the left of it is less than that element, or maybe less than or equal to, and everything to the right of that element is greater than that element. So I can do insertions like this into a binary search tree, and you get something that looks a little bit like this in terms of being in order. But one of the problems here is this can go very badly at a certain point. Let's say these elements are in order. So if we have 1, 2, 3, 4, for example, you get a line like this. And so you'll actually have linear depth, which is really bad for doing queries and things. You can also get the bad runtime other ways. So let's say I did something like 1, 4, maybe, yeah, 1, 4, 2, 3. Or if I ended up adding more elements, and use 1, 6, 2, 5, 3, 4. You see, I'm just going the min element, max element, min element, max element, alternating back and forth. You get this zigzag pattern. So you can get some fairly complicated linear time or linear depth trees. Something like this. So we want to avoid these. And it turns out if you randomly permute the elements that you're inserting, so if I just, here's me being somewhat random, something like that, you end up getting something that's fairly balanced. So 5, 3, I guess these aren't, okay, that's not too balanced. Let's do, just want to draw a balanced tree, I think. Something like this. You end up getting 3, 5, 2, 4, 6, and 1. Something like that. And so we end up getting something a little more fairly balanced if you permute them randomly. So to construct a random binary search tree is you just, step 1 is permute the elements. And step 2 is construct the tree. And that's all a random binary search tree ends up doing. But it actually gets a little bit more complicated for this data structure because we don't necessarily control the order that these things come in. We could have actually had these in this order, and this would be a really bad runtime for us. We can't change things as we go. So what we want to do is we want to get something that can do insertions online, but the goal is to construct that random order binary search tree. And so I'm just going to show you how we end up going about that. So we can end up getting these random insertions without doing anything fancy. There's these two names that get thrown around. You may have seen these. So you have these things called Cartesian trees. And so this paper came first. I think it came in the 70s. So there's this paper about Cartesian trees. Basically, the idea is to think about these things as XY points, like our Cartesian grid. Take XY points and turn them into a binary search tree. And then that's what a Cartesian tree is. And then later, there's something that's almost the exact same idea. There's a thing called Treaps. And so the idea of a Treap, this is also is very similar, was to marry the two ideas of a tree, so like a BST type tree, binary search tree, and heap, something with these heap orderings. And then that will form a data structure. And you'll see that the thinking, like the concept is very different in terms of what they were thinking about, but the data structure ends up being almost the exact same thing. And so for me, I kind of think of Treaps as like the data structure. And this is more like how to organize data in a tree, which I guess could be like a data structure. But yeah, maybe abstract data structure or something. Maybe not the best mental mapping, but oh well. So let's talk a little bit about like this marriage of trees and heaps. So this is a heap example. This is a min heap. And so the main thing you should notice about this is this value v goes above a and b for everything in the subtree. In other words, I can just write out v is less than or equal to the min of a and b. And then we have a binary search tree on the right that I'll draw. And we end up getting something like this. If we have this node v and it has two children, a and b, then the only condition we're really requiring for every node is a is less than or equal to v is less than or equal to b. Okay, so all you end up doing is you combine them. So let's say instead of sorting individual numbers, we're going to sort tuples. So I'll just write some out here, or not sort, but put them in a tree. Something like that. So what we're going to do in terms of the Treap data structure, the one on the left is going to be the key, and the one on the right is going to be the priority. So this is the heap value. So I'm going to be minimizing on priority. And this is the key value. That's going to be how I sort my BST. In terms of like the Cartesian tree, you can think of it as like X and Y. And so you can see how this mapping works like this. So we can actually construct these in a not that fancy way. So I'm just going to write out a naive construction right here. And so the naive construction looks something like this. I just look for the node that has the smallest priority, and I make that the root. It's always going to be the root because it needs to maintain that heap data structure, and everything else is an ancestor of it, so that makes sense. So I'll just write out 8.2, put it at the top. And then I continue on in this fashion. I just go in that priority order. So if I come out to the left here, I get 1.4. The next element I wanted to introduce was this 6.6. So I'll go do that one now. And then the next one I want to do to the left here is 5.8. So I end up having data structure formed this way, and I end up getting this Treap. Notice if by inserting things in this order, it uniquely just defines this tree. There's no decision that has to be made. I have that binary search tree decision. If I have an order I'm inserting elements, it ends up forming this tree exactly. So this is a naive construction. You can actually construct any Cartesian tree, even like something that's ridiculously unbalanced in linear time. So the construction I did just here, where I just like follow the nodes and go all the way down and construct it in linear time. I think you can. I think you can do it in linear time. You can definitely do it in log n, and it's got a little bit in common with spanning trees, I think, if I remember correctly. So maybe in the future I'll do something on that. But we have a slight problem in terms of, oh, well, before I get to that. So that's basically the idea of Cartesian trees. But if we go to this Treap data structure, the thing that makes it a balanced binary search tree is we just randomize the priorities. And just to make the analysis a little bit simpler, I want to show you how I map this to inserting things into binary search trees in random orders. Is if I just take the permutation of the numbers 1 through n, and these were just assigned randomly. then the tree I end up with here is going to end up being exactly that binary search tree. So if I order them in the order that my random numbers were given in the Treap up here, I get 8, 1, 6, 5. And if I were to just insert things in this order, I get 8, 1, and then 6, and then 5. So something like that. So if I can randomize this permutation, and so it doesn't necessarily have to be a permutation. I can just randomly pick elements in a really large range. Then I basically get a natural permutation of these elements, and I can insert. It'll be just as if I was inserting them into this binary search tree in this weird order. Okay, so here's one thing that changes everything. Is the insertions are dynamic. In other words, we don't get to pick that we put in 8 first. We might have to put in 1 first, or these numbers might be coming in order. So if we have something like 1, 2, so I'll just put these in permutation order. 8, 1, 5, 8, and 6, 6. If I insert 1, 2 beforehand, and then I insert 8, 1 over here, notice that it's not maintaining that heap property anymore. 2 is supposed to be smaller than 1. This breaks it. So with any good balanced binary search tree, so you'll typically see them as BBSTs, you do some kind of rebalancing based on rotations. So here's how the rebalancing works. And it's just based on these tree rotations. So we'll end up in cases like this. We have some number y, and we have some element x. And there could be a subtree over here. I'll call this C. There could be a subtree over here. I'll call this A. And there could be a subtree over here and call this B. Now, there could be things above me that come into me, but I'm not going to worry about that now. And the goal is we want to put x on top of y because x has that lower priority. But the problem is we have to also maintain this search tree criteria where x is less than y in the search tree criteria. So x, this is basically the only case that can occur. We also have another property to maintain is basically everything in A has to be less than or equal to x, has to be less than or equal to everything in B, has to be less than or equal to y, and has to be less than or equal to everything in C. So I'll just stab the elements in here. And that's what the tree rotation looks like. And so this is called a right rotation. So when you're implementing this in code, if you're doing a Treap and doing these rotations, you have to manage your pointers fairly well and just make sure that the right thing gets hooked up to the other piece. So basically what happens here is I just get rid of this piece. It hooks up to y, so y comes down. I have to hold on to b in terms of my code. And then I just stick b as the left pointer of y. And that's how I do my rotation conceptually. Okay, so let's do, there's also this notion of left rotation. So this could be the other case. We have x and y like this. We end up having A, B, and C. I do a left rotation. I want the exact same goal. This time I want y to become above x because it has lower priority. I end up getting something like this. A, B, C. And so that is a right rotation, or left rotation. And so you can kind of see, like, the reason it's called left rotation is I just think of it like that. Y is coming up above X, and the reason it's a right rotation, X is coming up above Y. So that's that left and right. Okay, I want to take a quick look at questions because there seems to be a lot of chat on the channel. Shouldn't 6 be in the left subtree? Ooh. Yeah, I don't think I messed that up. Oh well, maybe it was a little bit too far back. Yes, and another thing to mention in terms of these insertions is like that parent pointer. If you end up having parent pointers, this can get really complicated. So typically, if I'm dealing with Treaps, I don't like to deal with the parent pointers. But there's another data structure which we'll be going over soon called splay tree. And the easiest way to implement it is with parent pointers. And it does a lot of the same things that Treaps do. Okay, so I want to do an insertion and show you what this insertion looks like. So what I'm going to do is I'm just going to make a fairly complicated binary search tree already. Something like that. And then I'm just going to insert this node 7 into the binary search tree. But then I'm going to end up giving it a really low priority. Let's say it's priority 1. And so I know that everything else comes before it. So it'll basically move up to the top of the tree. So if I insert 7, it goes right here in the binary search tree. So it's greater than 5, it's less than 8, greater than 6, ends up going into 7. So I need to perform a left rotation to put 7 above 6. So it ends up looking like this. So I'll just copy this over. Ooh, that is not the thing I was copying. Try that again. Good. Okay, so I just delete these two and I do that left rotation. So I get 7 and then 6. If I do the next rotation again, going like this, I'm going to push 7 up above 8. So again, this is A, this is B, this is C in terms of this rotation. I feel like I lost a node. Maybe I didn't. So that subtree stays the same. The only thing that moves is B, but B really didn't exist. So yeah, I just cut the pointer here, move this piece down, move this piece up. E. And get something like that. And then I can do one more rotation. So this is A, this is B, and this piece right here is C, if I'm doing my left rotation. So I'll copy all these pieces again. So I want to put 7 at the top. So I'll just move 7 up, get rid of that pointer, move this piece down, but 5 has to become the subchild of 6. So I'll need to put this in a temporary pointer somewhere. But then 5 becomes the subchild of 6. And then 6 goes over here. Then move it back. And so I can do a bunch of tree rotations like this and get to any state that I want just through a series of tree rotations. Just pushing the changes up the tree. And eventually, so my ancestors are going to be in sorted order by priorities going down the tree. So maybe this is the priorities if I'm going down the tree. And so if I just insert myself here and let's say my priority was 7, well, I'm going to end up bubbling up the tree until I end up getting to my insertion point in the Cartesian tree at some point. And so it's always going to end up working out somewhere in the middle. Yeah. And as like every single operation, both the binary search tree and the Treap properties are maintained. It gets maintained throughout the data structure, which is really nice. Okay, so here's the powerful piece of Treaps. In terms of this data structure, this is the thing that just makes them really useful, is that you can split a Treap in log n time. So the idea is if we think of data structures basically just storing some kind of sequence, so every binary search tree is just like encoding some sequence that it's holding on to. We want to be able to take some element X where I want to insert things and just split it into 2 trees where this is everything that's less than or equal to X and this is everything that's greater than X. Something like that. So how do we do that? How do we get things to work? Well, we just insert a node with really low priority. So what'll happen is it'll do this bubbling up. So let's say instead of having priority 7, this thing had -1, then it's going to bubble all the way up to the top of the tree and become the root. And if it becomes the root, it looks like this. So here's my X. If I make that the root, well, then the binary search tree property is maintained. This is going to be everything less than or equal to X. And this is going to be everything greater than X. So without doing any extra work, just having an insertion, if I just insert something with a ridiculously low priority, I can split the tree in half in log n time. And that's because the insertion on a binary search tree, the runtime is based on the depth. And so a split is just an insertion now. So a split is just log n runtime. So I should mention that when you insert, if you end up having a random ordered binary search tree, insertion is going to be log n as expected behavior, but it's also like the depth of the tree is going to be log n expected behavior, but also with really high probability it's going to be log n. So it could happen that your tree gets like really, really imbalanced, but it's actually more likely that your computer has hardware failure. So this is why I end up trusting into in Treaps as a randomized data structure, as long as you're selecting your probabilities from a big enough range. And the other thing I want to mention about this analysis is you basically have to assume that there's no 2 priorities that are the same. So in practice, what I typically do is just select something from this range. Or from 0 to integer dot max value. And that ends up giving you a fairly low probability of collision. And it's okay if you have like 1 or 2 collisions in practice, how this thing kind of works out. Okay, so this will allow me to do a split in log n time. Let's talk about another operation called meld. So if you split a binary search tree, it's not that useful if you can't put it back together. So that's the idea with meld. We basically, let's say we have 2 different subtrees like this, and we want to stick them together. So maybe this is glue or solder or something like that. So we're just stitching our 2 arrays back together. That's the idea with this meld operation, is you have 2 subtrees. You know that everything on the left is less than or equal to everything on the right, and you want to stick them together. And so this differs from a thing I like to call merge. So there's a reason I don't call it merge, is let's say your array represented, or your tree represented this range, and you had another tree representing this range. and you had some elements that overlapped. So maybe your array looked like something 1, 2, 8, 21. And then your second array looked something like 4, 6, 9, 24, 81. You'll notice that there's a range overlap between these two parts, right? So this is where things get messy in terms of the merge. And it also makes the runtime a lot more complicated. Where melds you're going to see is actually really efficient. So that's the conceptual difference between these two operations. Sometimes I've heard this called join, but I like the idea that you're like soldering the two pieces together. So that's why I call it a meld. Yeah, so the only thing that needs to occur as a precondition before doing a meld is you end up having A and B. You want everything that's in A to be less than or equal to everything that's in B. Something like that. Okay, so now we can meld these two pieces together. How does that look? So let's say we have a binary search tree. That's not right. And then we have another one. Now, they have to be disjoint. So let's do 16. 10, 21 over here. And we want to meld these two together. So they're going to have different priorities. Something like this. So maybe this is how I write out my priorities. So those are my heap orderings. I want to end up with a search tree that basically has the right heap orderings and then the search tree criteria. So one thing that you'll need to notice is if we're looking at these two roots, like if it's coming into this meld function, so our meld function is going to be take in two subtrees. So we have subtree A and subtree B, right? And we want to meld these two together. If I look at these two different trees, this has a much lower priority than this one, but I also already know that everything in A is going to be less than or equal to, or less than everything in B. So maybe it should actually be strictly less, but we'll talk about how you get around that later. So I know everything's going to be less on the left than on the right. So what we end up wanting to do to stick these two together is only care about these priorities. So whichever one has the lower priority is going to end up being the parent. So we'll put that here. And then 2 is over here. So then now we have two subtrees that we have to still meld. We have to put something together over here. It's going to be this subtree and this subtree, potentially, sticking those two pieces together. So I just call meld again. Whatever the result of meld is for this one going in here and this one going in here is going to be that subtree. And that's how I'm thinking about it. So I'm just recursively calling it at every single step, stitching the two together, and then coming back up the tree. So I'll call meld here. 16 ends up being the priority here. And so I end up getting, keep this piece over here, which is 21 and 4. But then now I'm left with this other dilemma. I have to decide between 10 and this subtree over here. And so I go down this subtree. 10 will become the root, the results of that meld. And then I just stick the one on the left over here. So I can basically meld these two trees in log n time. So let's talk about why it's log n. Basically, I'm walking down some path in the tree. I don't know which path I'm walking down, but I'm walking down two paths in each of these trees. I'm either reducing, taking away the root on one or taking away the root on the other. So the runtime is just going to be whatever the depth of A was plus whatever the depth of B was in terms of the number of nodes I touch. So I stick these two pieces together. So the runtime is just this. And that's just the expected depth. Okay, so now I can split and merge binary search trees. Let's get to the idea that we want to do. So a binary search tree can store a sequence. Well, I can actually split multiple times. Like I could do a split on the binary search tree. And let's say this is X, right? So X goes into the binary search tree. I get something over here, which is A. And then I end up having something here, which is B. So I have A and B in terms of my X and A and B over here. So then what I can do is on B, I can call split again, and I'll call it Y. Okay, so now I split that. I'll call this middle piece B. I'll call this middle piece C. So I end up having Y. I have B, and then I have C. B is the interval from X to Y. So what we basically ended up doing here was we can split the tree twice, and you end up with an interval that's being represented, and that's going to be the subtree B. And so this runtime is still pretty good because the split operations are of 1. And then if I want to put this Treap back together, I can just meld these two pieces together here. I'll end up getting one subtree and then meld these two pieces here and put that back together. Okay, so how does that help me? So with a Treap, another thing we can do is we're basically just storing these indices. So what I could do to make my life a little easier is these indices could be like array indices. My Treap. And I could end up putting a value in the node. So my values could be something like 1, 5, 2, 3, and 4. And then I could perform splits by selecting things that are right in between here. So sometimes what I like to do is put an ID on the nodes so I can split like right before an element or right after an element. So I could insert an X right here and insert a Y right here. And now I have this interval. And if I want to do something like an increment, or actually let's just do a subtree minimum, what I can do is I can store a subtree aggregate. So let's say my nodes, my tree looks something like this. Let's do 2 to 4. These are my keys. Now what I can say is, let's say the values were 5, 3, and 2. I can also store a minimum value. So what's the minimum for this entire subtree? Subtree here. The node basically stores a few pieces of information. It stores like the left and right pointers of its tree. It stores the key. It stores the value. And just like a segment tree, I can store the min of the subtree. So I can know for the entire subtree what that minimum value is. So let's make this a little bit bigger. So let's see, these were my key values. My min for this subtree would just be 1. My min for this subtree would be 3, and the min of its 2 children. So this is also 1. The same thing over here, this one's 5. And the min here would be the min of its value and each of its children. So this would be 1. So since if I maintain this in this lazy fashion, every time I do tree rotations, if I do a propagate and then an update, just like I did for segment tree, I can just look at the root node of this tree B, and I could know what's the min of that entire range. So this is just how you end up getting a Treap that ends up doing subtree minimums. And it's pretty simple to code in that way. So you can end up doing the split. So it's way more work, but then you can actually modify it a little bit more. So what I want to start working towards is show you a few more things. Okay, so let's say we want to delete from the tree. Oh yeah, also one more thing. You can also do lazy propagation. So one thing I could do is I could have a delta change here with 4, and I could increment everything in this subtree. And every time I touch this node, I could propagate that delta down to its children, so I can get exactly the segment tree behavior in terms of the Treap. Okay, so let's talk about one more operation. Let's do delete. So let's say I have something like 3, 8, 6, and then I have 7, 4, something like that. And let's say I want to, what I do first is I run a search down to the tree, find node 8. If I want to remove it from the tree, I just delete that node and then call meld on the 2 children. It's a pretty simple operation. So delete becomes really simple if you have a good meld function. You don't have to add a lot of different things. So I pretty much always code meld if I want it just for binary search tree use cases. Okay. So I want to talk a little bit about data structure. Actually, before we go back, I want to take a look at the comments and see what's happening. Yeah, so a lot of people are getting ahead. But the thing I want to do with the Treap here is implement a string. So what we're going to do is we're going to talk about a rope data structure. And I want to implement a rope data structure with a string, representing it as a string. So for our rope, what we want to do is we just want a string. And we want to be able to do the following operations. So what I want to be able to do is insert a character into a string. And so what that could be is, let's say I have like banana. I could say I want to move NA to the right and then insert X into banana. Another one I'd want to be able to delete a character from the string. So similarly, I might want to do something like for banana, just delete the X and then move this piece back to the right. And the last piece is I want to be able to move pieces around. So I could have something like this. What I may want to do is remove a chunk of my string, move this piece over here, and then move this piece into place here. So this is good if you want to do like card reshuffling or card rebalancing. And so the kick here is I want to be able to do all of these in log n time. That's really the goal of this rope data structure. So if we have a string like banana, in terms of a binary search tree, we don't really want to have banana in order. What we want is a binary search tree in this form. So maybe I pick a different string. Maybe I pick binary. What I really want is I want a tree that is an in-order traversal of binary. So if I do an in-order traversal of this tree, what you'll notice is I'll get out something that spells binary. But then I have a problem. If I want to insert X, I have to figure out how to insert X into this tree. So where does that end up going? Well, there are a couple places X could go if this is a normal insert in binary tree before I do any rotations. And that's going to be all the null nodes in the tree. So maybe I changed my pen color. So these are all the places it can go. And so you'll notice that these leaves right here all correspond to insert locations for binary. So if I write out binary, a little more space, if I take the leftmost insertion point, it would insert it before the B. If I take the one a little bit to the right of that, it inserts it here, 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 and here. And so these are all the different insertion points that I could insert anything into binary as I'm going down. So what we're going to do is we're actually not going to make a binary search tree. Instead, we're going to insert things based on this thing called implicit indexing. In other words, let's say we want to insert something into position 3, which would be right here in the tree. Then I would want to be able to very quickly find that this is the insertion point, and then just drop the piece in terms of position 3. And then if I put X here, if you do the in-order traversal, you'll notice that it's in the correct order. Like X is properly inserted. And then I could do tree rebalancing and everything will fall back into place. Okay, so now all we need is a convenient way to walk down the tree and then get down to one of these leaf nodes that are the appropriate insertion point. That's what I really want to get down to at the very bottom. So what we're going to do is just store subtree sizes. So if I look at my tree binary, we get something like this. I just store the subtree size in the node. So this one ends up being 1, this one ends up being 1, this one ends up being 3, 1, 2, and then 6, something like that. And so then I want to know exactly where to insert things. So I basically know from the size of the subtree how many leaves are in that subtree. So if I have something like just B, it ends up being the size of the subtree plus 1, the number of nodes in the subtree plus 1. So if I'm inserting something like 0 or 1, then I want to go down this subtree because it's going to either be over here or over here. But if I insert something like, let's take a look at an example. Let's say there's something like a subtree A, subtree B, and I'm at X. And I need to figure out where my insertion point is. If I have 8 things over here and 9 things over here in this subtree, and I'm inserting into position 8, well, position 8, if I'm doing 0 indexing, would come after all of these. So I'd actually have to go down to the right subtree and insert into the leftmost piece of right. So what you end up doing is you end up making a similar call to that. But you also have to say, okay, well, I've already evaluated everything that's in the left subtree. There were 8 possible options. So now I change my index to be position 0. So I can insert position 0 in the right subtree. And now I end up having that insertion into the right subtree. So we'll do a quick example with banana, or with this binary example. I'll insert into position 4. Yep. And I'll insert X. So the subtrees were like this. Okay, so I want to insert X into position 4. So I look at the left subtree, it ends up having, or position 3 rather. I look at the left subtree, ends up having, yeah, I'll do position 4. So the goal is to get down here. So I look at the left subtree, I see that it ends up having 3 things. 3 things in it. And that's not enough slots for me to go down that piece. And so there were 4 possible options to my left. So now I change the index to be 0, and I instead go down the right subtree. I look at the left subtree, which is size 0, and the right subtree, which is size 1. And I look at this X, and I see at this point, I can insert X here on the left because there's nothing that goes there. I could, yeah, just walk down the tree in that fashion. So that's how I can do dynamic insertion. And I can maintain the subtree sizes just like I was maintaining the mins. I can just store the number of nodes in each of those subtrees and propagate them up. Okay, so if I want to delete a node from a string, it's very similar. I basically just store the subtree sizes again. Get rid of these pieces. Yeek. And so if I want to delete from position 0, so this would be position 0, 1, 2, 3, 4, 5. I basically just want to find where it is in the subtree, and that's where I end up doing my deletion. So I end up getting the number of things that are left of me. That's 3. I'm the 4th element. And then I have some number of things to the right of me. So if I'm doing my delete, I just make sure that the position I'm deleting from, if it's less than the size of the subtree, I go down that subtree looking to delete. If it's exactly the same as that subtree size plus 1, then I need to delete the node that I'm currently at. Otherwise, I go down the right subtree looking to do delete. And then now for the moving pieces around piece. I could end up having X, Y, Z, A, B, C, X, Y, Z. If I want to move pieces around, well, I can just do a split on the Treap here and a split on the Treap here by doing one of those insertions that I already showed you how to do. And so what I'll end up getting is I'll do alpha and beta. I'll end up getting a tree that looks something like this. I have alpha, I have beta, and then I have A, B, and C, and that corresponds with A, B, and C here. What I can then do is take B out, and let's say I want to put this chunk at the end, so I want ABC at the end. Well, then what I can do is I can call meld on C and B, something like that, and I am getting a tree, and then I call meld on A. And if you recall, meld didn't look at any of the keys in the binary search tree. That was the big trick. Meld only looked at the relative ordering. Remember, it required that if you called meld, everything in C better come before everything in B. So if we're not even looking at the keys to doing ordering, if we're doing the insertion, then this works perfectly fine. In fact, you don't have to code a special insertion function if you do implicit indexing. If you want to build a string like banana, you basically call meld on B and A, and then meld on BA and then N, and then you keep going on and on. You just treat the single characters you're doing the additions on as the right subtree and meld. You can stick all these together. You end up getting a string that is a binary search tree that represents that string. So that works pretty well. Yep. So the string concatenation is log n time because the meld operation is O of log n. That's exactly right. So we can end up doing just any kind of concatenation operation just by doing these melds with a treap. So it ends up being really efficient and really powerful. Okay. And so the last piece I want to do today is I want to talk about one more operation that I could perform on Treap that I think is pretty powerful. And that's if I have something like binary in terms of my rope, I can select an entire subtree, or not entire subtree, but an entire substring, and then reverse it in log n time. So this would be a really cool string data structure if I could just select a chunk of my binary tree, the binary string, and then just reverse it. Well, I already know I can do a split. So I could take binary and I could write the split code and do something like this. And I can just cut out this piece. And what I'll end up getting is I'll get a tree that looks something like this. I have my alpha and beta, something like that. And over here is just the tree that contains B. Over here is the tree that contains inair. And over here is the tree that contains Y. Right? So I could do this operation. So now what I want to do is be able to do a flip. So what I do with my node is I've already got all that other information. I have like the character that's there. I have left and right. What I'm basically going to add to my node is a flip. And so it's a flip bit. And it's basically going to say, is the subtree flipped or not? Yes or no. So I could have something like maybe my tree looks like this. All I have to do to say it's flipped is just set this flip bit. And so now when I do lazy propagation, I end up with a neat case like this. So if I have X and then I have my two subtrees, A and B, if this flip bit is on, all I have to do when I do my lazy propagation, when I touch this node again, is flip the bit to off, like I've touched this node, switch the two subtrees, B and A, and then flip those bits on. And so now through the magic of lazy propagation, I can even take a string and flip entire subtrees of this string, and it just amortizes out with lazy propagation. Because all of these operations that we've seen so far, the split and the melds, they're all expected log n runtime. So my flipping operation like this will also be log n runtime. Yeah, so for example, in this case, I push this change down, those bits flip, my I would come over here, and then my AR would come over here. Like this. And then if at some later point I try pushing, so maybe I push that change down, it goes to the leaf nodes. I push this change down, then the R comes over here, that goes away. So then I've got the exact same tree, but in reverse. And what's nice is if you flip a tree twice, so if I flip this tree and then I come down later, propagate it, flip it again, the flip bit could turn on and off and on and off, and I don't have to do all that extra work of maintaining the flip state. I can just encode it in lazy propagation. Yep. Yeah, and so it's a really powerful data structure. I guess maybe I'll go over one more trick. So you have, these are all basically all the basic things you can do. That's a rope. I really like implicit indexing. It's really nice to be able to slide things around. If you do explicit indexing, though, another thing you can do is, like, let's say these are the indices. And so you can have sparse indices. So maybe this is like 100, and this is like 200. One thing I really like doing in certain problems is I could select the upper range. So I could basically call split here, select the upper range of this binary search tree, but maybe I want to increment something in this range. So maybe I want to move everything up by 100 in index. So I'm not incrementing the values here, I'm incrementing the indices. So I could actually do something where I slide the indices of my nodes. And so now these are my new indices. And then I could meld it back together. You have to be a little bit careful when you do that kind of meld, though, because if I try to do the increment of indices at a different point in my tree, let's say I do that here and I increment them by 200, I no longer have that property because this becomes 201, this becomes 203, this becomes 208. Now I don't have that property that, remember, this is A and over here is B. So 109, 200, 300. I no longer have that property where A is less than or A is less than B. That's no longer the case. So I can't do a meld anymore, and then I have to do a merge, and it gets really slow. So typically, if you want to slide the indices around, you're typically increasing the right-hand side. So I've used that before in problems where I've basically had some indices. I wanted to slide an entire set of indices on the upper bound by some amount, and I just continually slid them to the right and incremented them. Yeah, and it was easier to think about for those kind of problems. Okay, so I'll answer a few questions and then end the episode. Yeah, so wasn't aware that login was possible for reversing. Where can I find more such tricks? I think it's just seeing a lot of problems and realizing like the operations that Treaps can provide. So they're a lot like segment trees, except you can also manipulate the structure as the biggest thing that changes in a Treap. That's where, like, if I feel like I need to move things around at all or reverse them or slide them, that's when I start thinking about Treaps over segment trees. But yeah, I don't have like a really good comprehensive list of like Treap tricks. This was just more supposed to be an introduction. The other thing is I'm going to try to find a few representative Treap problems for the next few episodes, and I'm going to actually code a Treap from scratch. You'll see how that works. You'll see like some of the design choices I make. And I'm actually going to code it two ways. There's going to be one I mentioned right here, which I think is a little more conceptually easy to understand. And then there's the one that's what I call the Russian Treap that does the splits without inserting nodes. And I see that a lot in Russian coders code, and I really like it. And I want to show both versions. So another question is, do I use a template for Treap, or do I just replace some parts during the contest? Yep, that's exactly what I do. I have some representative code for a Treap, and I just modify it. It's kind of like I have representative code for my segment tree, and I just modify it as I need it. So basically, in the Algorithms Live episodes, like the future ones, the plan is going to be code a Treap from scratch. I think I might do an episode where I code a rope. And then I'm going to do a handful of other problems where I'm just going to pull out the Treap and use the same Treap and you'll just see how I modify it. And it'll maybe be a little easier to see. Giving links on practice problems for Treaps. I'm actually still looking to collect some good Treap problems. So if you happen to know any problems that have been solved with Treaps, I'm going to do those. There's a really good problem from Central European that I'm going to do in a future week. It's like Central European Regional Contest, I think 2007, might be 2006. It's called Robotic Sort. And I'm going to do that one with a Treap. I think that one's going to be really fun to solve. I'm also going to code this rope. I think next week what I'll do is I'm going to code the rope data structure. And the week after that, I'll code robotic sort. Another thing is, I also really like splay trees. A splay tree can basically do everything a Treap can do, with a little bit differences on the analysis and how they work. So I'll go over those as well, and you can basically pick between which one you want to use, because you could also code robotic sort with a splay tree, or anything like that. Yes, and then links for resources for further reading. Yes, so I'll share the links for the Brian Dean paper and the Jeff Erickson notes and a bunch of other things on the blog right after I run this episode, So, yep. Thanks to everyone for watching. I hope you can start working Treaps into your problem solving, solve a few Treap problems, and make this a useful data structure for yourself. Yeah, and I look forward to coding more Treaps in future weeks.